So, time for actually doing it. Let's solve the inverse kinematics for this robot. Once again, we want to solve the inverse kinematics for these 2 degrees of freedom, position x, y for the end effector, right? I put the axis here as well, x, y, so it's clear. This means I take these 2 equations, so from the right side of the forward kinematics, and I'm trying to come up with equations for convert this into something q1 equals to a function of the 2 positions and q2 another function on the 2 positions. All right. Any ideas? How can I convert this into, let's say, simple example, we had px equal to this, just L1 cosinus q1. What could I do?
I can separate C1.
Separate C1?
Yes.
What do you? It would be L1 on the other side, and then the inverse of cosine, so r cosine, that thing, right? I cannot do this. That would be nice. Sometimes in some robots we might get this nice easy relationships, but today is not the day. Same thing here. I have S1, I have S1 plus SQ1 plus Q2. What else could I do? Any ideas? We're gonna have to remember some trigonometric relationships.
Wasn't there a formula for the sum of cosinus?
Sum of cosinus, so cosinus, basically the formulas that we're gonna need, q1 plus q2, sinus, q1 plus q2. This is also pretty useful of anything. Is what? 1. What is this one? 1 by 1. Cosinus.
Cos q1 times cos q2 plus minus sin.
And this one is? What?
Sine q1 cos.
This one is 2.
C2,
Yeah, plus
right?
sine 2s2. I'm not sure.
No? Bada.
My intuition says yes, but
It's correct.
it's correct.
I'm not, don't remember these things by heart as well, but yeah. All right. Do we have anything here? We have this one here.
But if we multiply
If we make what?
the second one with the minus and add it, so first one.
So this minus this, px minus this one, px minus py. We can vector factor out L1 and L2, but it would be nicer if we factor out cosinus, sinus, because factoring out the lengths, yeah.
Try to reduce the make something like with px minus py to assume that we have L2 times cosine 1, 2 minus sine 1, 2 plus L1 giving common factor.
I lost you.
To reduce one from the other. To reduce py with px.
Like replace, how to reduce it? Adding them would get me something maybe. Let's see, px plus py. Or subtract them, we'll see. So basically if I add these two, I'll factor out L2 and I'll have C12 plus S12, right? Plus L1 C1 plus S1. Right, this is similar to that. I mean, with the plus or minus, doesn't make much of a difference. Let's say, so this can be basically cosinus Q1 minus Q2. Sorry, no, this is not it. No, because it's not sinus 1 times sinus 2. Yeah. So what do I do with this? Not much. Sorry? Multiply them? Px times py, I would get a lot of, I think I would mix things even more because I would get things like this and C1 times CS1 and also C12 S1 and S12. So if you might forget L1, L2, I'll get something like this, C1, S2, S1, S2, C1. So I think this is going to be even more things I have to clear out eventually. What, I'll give you the first hint. What if I square them?
Each of them?
Yeah. So px square. What will I get? All right, plus L2 C12 square plus 2 L1 L2 C1, not square, C12, not square, right? S12 square plus 2 L1 L2 S1 S12. What do I get if I add these two?
We will have cos squared.
We will have like L1 square plus L2 square.
So C1 square plus S1 square gives me 1. Great. So I'll have px square plus py square L1 square. So I got rid of this trigonometrical. L2 square, also the, these ones, because it's cosinus of Q1 plus Q2, sinus Q1 plus Q2, same quantity, plus of C1, C12 plus S1, S12. This can go here. This can go under. So we have all the trigonometrical stuff there and all the knowns here. Sorry. It's minus because it got this way. What about this one? What identity are you using? The first one, right? Because we have A, B. So I will have here basically if this is with a minus, sorry, this is plus minus, this is minus plus. So this will be basically cosinus, and I'll write it fully. of what? Q1 minus Q1 minus Q2, or minus Q1 plus Q2. All right, so I have, this is my first angle, this is the second, Q1 plus Q2, and I take A minus B. I should have written here A and B, whatever. So this will be what? Cosinus of minus Q2. Which is equal to cosinus of Q2. All right, we got rid of Q1. All right, so what? How much is Q2 now? This is what I'm looking for. Sorry, Chief. All right, so this will be arc cosine of this will be Q2. And there it is, my first equation. I have Q2 as a function of position on X, position on Y. Right? So now, if I tell you I want to move the robot at some coordinates, you can tell me what should be the second joint coordinate. I tell you I want to move to Px0, Py1. You put the values here, you need to know the lengths of the robot, of course, and you can calculate Q2. All right? So we have it here as well. We square, and then using this one, we can solve for Q2 equals to this one. All right. First one is done. What about Q1? If we have Q1, then it should be simpler. Sorry?
Maybe we can replace the two. We can do the same, but to replacing the sum with the difference between px squared and py squared.
If I take the difference, I erased it now, but then I will not be able to simplify this because I will have cosinus square of something minus sinus square of something. I will not be able to take equals to 1. Good try.
Can we just replace Q2 equations and solve for it?
So I put Q2 here. So let's say I know this one now. It's not sinus 1, but it's sinus 1 something, star. Can I solve for Q1? If it was really the same sinus of Q1 here and there, then yeah, I would have been able to. But here, now basically I can replace Q2 with a function of, with my G, Px, Py. Right? So I can say sinus of Q1 plus G of Px, Py. Okay? But still I have something here and I cannot easily get rid of it. What if we try to apply those trigonometric identities here? Px would be what? L2 cosinus of Q1 plus Q2 would be trying to split out and trying to get Q1 away outside of the trigonometric function. So it's not inside Q1 plus Q2. Because that's difficult to divide, simplify, and so on. It's not possible. Sorry?
Can we solve it with this third equation if we, like before you erase? Instead of our cos, we just keep cos, take it to the second power, and then subtract one.
So this equation, All right, so what do we do with this equation?
We move cosinus back next to Q2,
Uh-huh.
then 1 minus Q cos of Q2 to the second power, it will give us sinus
Of Q2. You only have Q2 here. Now you got rid of Q1. So you'll need to bring it somehow back in.
yeah, but I'm thinking, so we calculate sin of Q2 and then we put it back into
In here. You still have to get rid of this one out somehow from the sinus so you can simplify things. Right? It's the same problem. It's not that I don't know sinus of Q2. Now let's say I know the value, because I have an analytical function for Q2. But I want to isolate Q1 now.
What if we subtract after we square? Not.
Yeah, that's what your colleague said. If we square and subtract, then we will not get rid of these terms here, because it's going to be cosinus of Q1 minus sine square minus sine of Q1 square. Before we got rid of them because they were plussed, right? Now they're not going to go away. So if we square and then subtract, we're going to have more terms. Let's try to expand these ones. So what would this be? This is basically what's written there, cosinus of, and let's do it like this in one step. Sinus, minus, sorry, right, plus L1 C1. And Py will be what? Sinus of Q1 plus Q2. Come on. Plus L2 cosinus 1 sinus 2 plus L1 S1. All right, let's factor the things we know, put them on one together with the things we don't know. Right, so this can be rewritten as, if I factor out C1, which I don't know, it will be what? L2 C2 plus L1 C1, correct? Minus L2 S2 S1 from here. Let's do the same thing down here. We will have L2 C2 plus L1 S1, right, plus, did I take it correct? It's with a plus, plus L2 S2 C1, right? And you see here I have the same term here, here, and here, here. Correct? Did I miss a minus somewhere? No, I did not. All right, so let's call this kappa 1, let's call this kappa 2. So then I can rewrite this kappa 1 C1 minus kappa 2 S1, kappa 1 S1 plus kappa 2 C1. And you see I start to get somewhere, right? That's how it is. Where kappa 1 is L2 C2 plus L1 and kappa 2 is L2 S2.
Now if we sum them again.
If we sum them again, what will I get? I'll get kappa 1 factored out, Q1 plus S1. Plus kappa 2 factored out C1 minus S1. So I'll have this thing. Let's do it. C1 plus S1 plus kappa 2 C1 minus S1. If they were with plus, maybe. What if we square them and add them? What will we get? What if I square this at the power of 2? What will I get? Kappa 1 C1 square plus kappa 2 S1 square minus 2 kappa 1 kappa 2 C1 S1. Correct? And what will I get from here if I power it 2? Kappa 1 square S1 square plus kappa 2 square C1 square, all right, plus 2 kappa 1 kappa 2 C1 S1. Are we getting somewhere? Where are we getting it? If I add these two, what happens? C1 S1 goes away, so I get kappa 1 square plus kappa 2 square, and that's it. Is this, no, that's not, yeah, this is px plus py squared, right? Because I took this, I rewrote it, again I squared them as I did before, and I added them. And what did I do? I got rid of my q1. I want my q1, I want some q1. Now I got rid of it too. Basically, if I expand this, I will end up to the same thing as here. All right, so the square of this, you will see it's going to be the same. So we shouldn't square and add. All right, it's a bit far-fetched, but it will make sense when we see the geometric solution. But basically, we define some new variables, sorry, and things will make more sense later. Arctangent of kappa 2, kappa 1. All right, so I define a distance, which is the square root of the sum of the squares of these two variables. This is something we know, right? It only depends on Q2, and we have solved Q2, so we know it as a function of px, py, right? And this is an angle as the arctangent of these two, right? If I write this, let me consult my notes because it's even for me to remember this by heart is tough. I can say basically that kappa 1 is equal to r cosinus of vita, and kappa 2 is r sinus of vita. Let's see why this makes sense. Basically, if I replace these two here, this will be true, because kappa 1 square plus kappa 2 square will be r square, right? Because this will be square plus this square, it will go away. So I will have r square here, square root, is going to be equal to r. So this holds up. And then if I take the arctangent of this one, it's going to be kappa 2 over kappa 1. Because kappa 2 over kappa 1. R will get simplified, so I'll have sinus of veta divided with cosinus of veta, which is tangent of veta. Arctangent of tangent of veta is veta. Right. Now, if I replace this here, what do I get? Where to write? So I'll take these two and replace them here, and then bring them here. What do I have? Kappa 1 r cosinus of vita cosinus of q1, and I factor out r so I don't have to rewrite it. Sinus of vita, sinus of 1, right? This is my px, and my py is again r cosinus of vita. Now it's sinus of 1 plus cosinus of vita, sinus of vita, sorry, and cosinus of 1. I forgot a bracket here, py. So I have r factored out, and I have this and this. What's next? What does this look like? There.
If we square them and then we add them.
No, we don't divide them yet. Sorry? The first one is, this is cosinus of vita minus q1, right? Sorry, plus q1. So px is basically r cosinus of vita plus q1, correct? Vita q1 minus vita q1. So if I have a minus here, it will be a plus in the cosinus, right? And this is which one? Cosinus, sinus, sinus, cosinus. It's basically the second one. So this will be what? Sinus of vita plus q1. All right? Now what? I have the same thing inside. Can I get rid of square and add them? Then I get rid of them for good. Again. Any ideas? What can I calculate if I have the sinus and the cosinus of something? The tangent. How do I calculate the tangent? I divide them, right? So if I divide py by px, what will I have? R will go away. I'll have tangent of vita plus q1. How do I take q1 out of there? Q1 will be what? Let's write it in one go. Arctangent of tan of py px minus vita. Is this a function of px py? Has py px here. What about b? Where is b? B is the arctangent of kappa 2, kappa 1. What is kappa 2 and kappa 1? Kappa 2 is L2 sinus of Q2. Kappa 1 is L2 cosinus Q2 plus L1. So this is a function of Py Px and Q2. But we know Q2 as a function of Px Py. So then in the end it's a function of Px and Py. But that's only because I have already solved for Q2, right? If we hadn't solved this, then it wouldn't have been good enough. It would have been still a function of Q1 and Q2. But we know Q2 as a function of Px Py, so I can go here and replace Q2 as a function of Py Px, and in the end I will have a very long equation for Q1 as a function of Px and Py. All right? Far-fetched, but you see even for 2 degrees of freedom, inverse kinematics can be complicated. It depends on how the axes are oriented and so on, like if they were prismatic joints or different orientations, it might have been more difficult, more easy, but yes, what I'm trying to show that even for 2 degrees of freedom on a plane, inverse kinematics can be tricky to calculate. So let's see what we have here. It's basically the same on the slides. So we have, just for completeness, are we there yet? Here we are. So we have Q1 as a function of y and x. Any questions?
For the exam, do we need to solve these kind of systems?
Yes. I mean, how simpler than 2 degrees of freedom you want? 1 degree of freedom?
0 degree of freedom.
0 degree of freedom, 0 in the grade as well. Go ahead.
In a real case, when we have a robot, can we, for example, approximate one of the direction of one joint to make the computation easier for the second one?
So for a real system, and what you'll see in the laboratory as well, is that you solve these equations numerically. What does that mean? It means basically I have a target. So this is an analytical solution. I have equations, and for whatever py, px I get as an input, I can calculate immediately, using the equation, what is the answer, right? We can solve the analytical kinematics for different types of robots. For the industrial ones, we can. But let's say for what you'll do in the lab, you will do numerical calculations, which means what? I solve the inverse kinematics for a specific pose. So I don't have like a general equation for any pose. I just do it for a target pose. So basically, I will replace some values here, and then the robotics toolbox that we use, for instance, has some methods that solves numerically these equations. So it basically tries different combinations, Q1 and Q2, until it finds a good match. You will learn more about, this is called basically optimization. You will learn more about this next semester if you do optimization. It depends on your line.
We do.
You do? Good. So you will see what I mean. I'm not going too much in depth because you will do next year, but yeah. There are different ways, not just wiggling around the values. There are obviously more smart ways to figure out faster what's the solution to this nonlinear system of equations for specific values. But yeah, it basically boils down to trying different values. All right. Another approach is using the Jacobian that we mentioned last week. I'm not presenting this either, but maybe I will put some resource on Teams so you see how this is done. It's basically with the Jacobian, if we have a starting position and I have a target position, I can calculate the velocity vector that takes me from here to the target position and do small steps and basically iteratively figure out what's the solution of the inverse kinematics to a certain pose. But again, these are numerical methods that only work for one pose, right? They're not analytical in the sense that we have an equation that gives me the answer for any pose. All right? Now, when I say it works for any pose, does it really work for any pose? Can I put whatever values I want here? And let's take the first joint solution. So, can I put anything I want here for x and y? No? Why not?
Because the robot needs to reach, so the position.
All right. So how does that get translated into the equation?
For example, Q1 cannot be equal to
Okay, let's say we have joint limits, but let's ignore that for now. Right? Can I put for Q2, let's say, can I calculate a value for Q2 for any value of X and Y? What's the constraint, or what doesn't let me?
Joint lengths.
Joint lengths, okay, but how do I see that in the equation?
It can be divided by 0.
It can be divided by 0, sure. But will this ever get to 0 for specific lengths? No, right?
We have a circle that is given by the square of x and y.
Yes. Y is a circle, because this thing will basically be able to reach a circle, right? That's the intuition. How do you get that from there?
X squared plus y squared.
You're going in the right direction. Okay, I cannot divide with 0. I have something that is not defined, right? It's not that, but it's something like that.
X squared plus y squared should be smaller than equal to 360.
Smaller or equal than?
360.
But X and Y is distances. 360 is degrees.
We can only put as much as the circle.
All right, good. Where do I get this from here?
From the length.
The lengths?
If,
Right.
if the robot is fully extended, then the sum of the lengths is the
And why is it a problem? If I have X square plus Y square bigger than the lengths, L1 square minus L2 square.
L1 and L2 do not be 0, basically.
I cannot reach further than my maximum.
All right, I cannot, but why? What function here has limits? Or I don't know.
Arc cos.
All right, what input can I give to arc cosinus? Can I give to arc cosinus minus 1 whatever value I want? No. What values can I give?
Pi over 2 and minus pi over 2.
No.
Is it like this?
So, what does cosinus? Can I give to cosinus whatever value I want?
Yes.
Any value, right? What will I get? The output is bounded. 1 and minus 1, right? So the arc cosinus can only take values in the range from minus 1 to 1. I will not have an answer to arc cosinus of minus 2. There is no value that I can give to cosinus that will return minus 2. That's what it says, right? So my arc cosinus has to be between 1 and minus 1. Or basically this quantity here has to be between minus 1 and 1, right? If I try to extend the length, the y and y beyond the L1 plus L2 square, I will get this division being bigger than 1 or smaller than minus 1, basically, right? So let's say if y is 0, x2 can only be up to square root of L1 plus L2, both of them squared. Yes, in that case it will be cosinus of 0. Anyway, so this is the one that limits my possible values for x and y. It's basically the arc cosinus, right, which cannot have input any value. Okay, if it was arc tangent, as we had here, because tangent gives results from minus pi over 2 to pi over 2 plus infinity. Right? You know how the tangent looks like? That's tangent, right? I mean, that's part of tangent. What's tangent of 90? Plus infinity or minus, depends where you approach it from. Okay.
Okay. But the solution is between.
Yes. The solution, no, it can, yes, it's between minus pi over 2, but plus k times pi, right? So the same thing as the solution for cosinus is also, I mean, the solution to our cosine is also minus pi to pi plus k times pi, whatever, because it can be, you have multiple solutions to our cosinus, but we usually take the one that is in the range of minus pi over 2 to, or minus pi to pi. All right. Let's see the geometric solution as well. And what does that mean? Because we don't have too much time yet. So another approach to solve this would be using geometry, which means what? I'll show this only on the slides so it goes a bit faster. And I have the figures there as well. So we can take basically this triangle here, right, where the tip, this corner is the tip of the end effector, right? And from this one will have coordinates x and y, right? That's the target pose. That's where I want to reach, right? So I can define this length here called r squared. I mean, the length is r. But it will respect the Pythagorean theorem, so r squared will be x squared plus y squared. And it will be basically this r here. Right? You remember at some point when we're doing this and we squared and summed, we ended up with r squared, right? That's why I said things might make more sense when we see the graphical representation. This is the r square. This is the same r square here. Right, good. So that's one thing. We can calculate this angle alpha using the cosine law. Maybe you remember it. It's another identity. It's not an identity, actually it's a way to calculate if you know two lengths and one angle. No, not the area. You can calculate, if you know 3 lengths, you can calculate, no, if you know 2 lengths and an angle, you can calculate the other length, right? So we know that this length here, r, or r square, will be L1 square plus L2 square minus 2 L1 L2 cosinus this angle. This is for any triangle, basically. It's the lengths that form the angle, and the angle itself can be used to calculate the opposite length. All right. So this basically tells me that A is this term here. All right. So I have to solve for A. And what is A? No, so this is basically r square. We saw it's x plus y square. So minus this. What is A? A is q2 pi minus q2, right? Because they're complementary. A plus q2 equals pi. So A is pi minus q2. This means that from here cosinus of pi minus q2 will be minus cosinus of q2. Therefore, this can be, I just multiply this with a minus, so I end up basically with this equation, which is the same as before. Q2, I erased it, but we had it, right? It was the same one. All right? So geometrically, I end up in the same result, makes sense. I should end up with the same result, right? Now, to figure out Q1, I calculate 2 more triangles. This one. All right, and from this one we know that the base of this triangle will be L2 cosinus of Q2, right? L2 is this length, Q2 is this length, and the height will be L2 sinus Q2, trigonometry, right? I also take this bigger triangle, and I'm trying to calculate B as the tangent of this height over this length. What is this height? L2 sinus Q2. Right? What is this? This side is L1 plus L2 cosinus Q2. Do you remember these terms? L2 C2 plus L1 was my kappa 1, and kappa 2 is the L2 sinus Q2. Right? And if you remember, we said that vita is the arctangent of kappa 2, kappa 1, and this is my vita. Right? It's the arctangent of kappa 2 and the kappa 1. So that's how we came up with this thing. All right. So if we go to our initial triangle, the big one, right, we know that the tangent of y over x will be equal to basically, yeah, the tangent of, I'll show you the big thing. So this is basically the angle. The tangent of y with x will be this angle, which happens to be q1 plus vita. Right? It's q1 plus vita. Right? So from here we end up in the same equation we ended up before. q1 equals arctangent of y over x minus vita, which is the arctangent of kappa 2 over kappa 1, which is L2 sinus 2, L1 plus L2 cosinus Q2. All right? And Q2, I put it here again. They both give the same result, obviously, makes sense. You choose what works best. Right, as I say, for the numerical solutions, you learn more, a little bit more in the lab, just how we actually use them, but how they actually, how do we solve it like low level, you will learn more next semester in the optimization methods. Right, so we completed the discussion on inverse kinematics, how we calculate it. Next week we'll see also how we use it in order to calculate trajectories, basically, which would be solving the inverse kinematics for many different poses and connecting them so that we follow a specific path. Any questions?